Let's talk about definite integrals with U-substitution. Definite, remember, means that we have a starting point and a stopping point. We're not just taking an antiderivative and getting a function back. We want an actual number in many cases. So here's a fairly simple problem, the integral 0 to 1 of sine of pi x dx. I've got it graphed here. What should we do first? You can probably guess because I've got my multicolored pens here. We want to do a lower bound. Degree a lower bound of 0 works. That's about the best we can do. How about an upper bound? The function tops out at 1 and has a width of 1. So a height of 1, width of 1 minus 0 is 1. And then a guess would be our kind of average of those two. So 1/2 times width of 1. And do you think the guess is higher or lower than the actual value of the integral? Well, if I kind of imagine this split into two and look at just this first half, I see this part where my guess is including the area, but it really shouldn't. And this part where the guess is missing the area, but it really should include it. And it seems like the guess is missing more area than I'm including by accident. So I think the guess is going to be too low. So I'm going to say that the guess is less than the actual area. Here's an interesting way to see that in another way. Let's redraw the curve. And the guess, so the guess is dividing that area of the rectangle into two parts. Two equal parts. Another way to divide a rectangle into two parts is by doing a triangle like that versus my rectangle like that. Do you agree that that lower triangle is half the area of the rectangle, and the sum of those two triangles is also half the area of the rectangle? And then that shows me that my guess is coming in below the curve I want, so that's more evidence that the guess is less than the actual. So that's fun, right? How should we take this integral? Well, we're in the U-substitution chapter, so I'm going to say U-substitution. What would you say for U? How about pi x? du equals derivative of pi x times dx, which is just pi dx. So 1 over pi du equals dx. So, oh, by the way, if I ever make a mistake, it's kind of your job to catch me, right? Sometimes the mistake is on purpose, sometimes it's not. We'll see. So this would be the integral 0 to 1 of sine of u times 1 over pi du. And let's stop and graph that. We hardly ever graph a u substitution once it's in the form of a u, but let's go ahead and try it. Sine of u is a sine wave, right? And here's pi, here's 2 pi. And I'm only going 0 to 1. And so I don't go all the way to pi here, and there's pi over 2, that's 1.5-ish, so I'm actually stopping here. So I'm saying this is the area I want, and that looks like a completely different shape than what we started out with here, even though really all I'm doing is changing the frequency. So it's a different shape. Now, shapes can change when you do U-substitution, but it should change in a way that kind of makes sense. And we're getting a hard cutoff here when we kind of didn't have one before. So it's not always bad to have a different shape, but it's a sign that there might be trouble going on. So we'll say it's probably trouble. So let's step back and think what might be going on here. Well, the original problem was basically the integral x equals 0 to x equals 1 sine of pi x dx. We don't typically write the variable of integration at the start and stop points, but in this case it really helps. When we transformed it here, so after the substitution, we had the integral of sine of u times 1 over pi du, and usually the variable of integration signified by dx or dt is where the x variable or t variable starts and stops. So what should really be going on here is the integral u equals something to u equals something else, and there's no guarantee that 0 and 1 are the right places to start and stop for u, even though they were for x. So what we need to do is translate the x start and stop into the u start and stop. So it's nice to make a little table that says when x is 0 and 1, what is u? Well, u is pi x. What is 0 of pi times 0? That's 0. Pi times 1, that's 1. So when I write this integral, I should really write u equals 0. Oh, sorry, that's pi, isn't it? I should really write u equals 0 to pi, not 0 to 1. So I should go u equals 0 to u equals pi sine of u times 1 over pi du. So let's graph what's going on there. Sine of u looks like that. And we're stopping at pi. So we're doing that whole area, which does look like the same basic shape as before, so it's less of a bad sign. So now let's finish this problem. Integral of sine is cosine? Negative cosine? Negative cosine, right? Negative cosine of u, and times 1 over pi. And I've taken the antiderivative, so now I write the closed square bracket. I could write an open square bracket there from u equals 0 to u equals 1. And now I can substitute in the u values. So I get, do you mind if I move the 1 over pi all the way out front? So minus cosine of 1, oh sorry, this was to u equals pi, wasn't it? Minus cosine of pi minus cosine of 0, which is 1 over pi. What's cosine of pi? It's negative 1, so I get negative 1 minus negative, and what's cosine of 0? It's 1. So altogether I get positive 1 plus 1, so I get 2 times 1 over pi, which is roughly 2/3, pi being roughly 3, right? So let's check that against our upper bound, lower bound, and guess. Our lower bound was 0, and we got something bigger than 0. Our upper bound was 1, and we got 2/3-ish, 2 over pi-ish. So we're below our lower bound, below our upper bound. And our guess was 1/2. 2/3 is a little bit bigger than 1/2, which is what we actually thought. So it looks like our new system gave us a reasonable answer here. So we can say lower bound check, upper bound check, and our guess was reasonable, and we even correctly predicted that our guess was less than the actual answer. So this is the actual answer. I was just doing this to make it easy to check against my upper bound and lower bound. All right, so that's the basics of doing U-substitution with definite integrals. You have to translate the x or t start and stop into the u start and stop, and then use that.